In module 4, we will discuss about fundamental matrix solution. So, what is a fundamental matrix solution? Its definition, along with some very good examples, some theorems. This is what we are going to discuss in this module. We now consider fundamental matrix solutions. You consider the system of linear equations given by equation 1, which is of the form dx dt or x dash is equal to at into x, where at is an n cross n matrix which is continuous on the interval I, and x is an n cross 1 column vector. If x1, x2 dot dot xn are n linearly independent solutions of equation 1, then the general solution xt is given by xt is equal to summation I equal to 1 to n ci xi t, which can be represented as some capital Xt into capital C, where C is a n cross 1 column vector C1 C2 dot dot Cn, and Xt is a matrix x1 x2 dot dot xn, which is a square matrix and whose columns are x1 x2 dot dot xn, the n solutions of equation 1. So, we define a matrix of n rows whose columns are solution of 1 is called a solution matrix of 1, and the matrix xt is called the fundamental matrix solution of 1 on the interval I if its columns form a set of n linearly independent solutions of x dot is equal to at into x on I. To have more clarity on these definitions, let us take an example. So, we have to show that capital Xt is equal to t square t 2 t 1 is a fundamental matrix for the system x dash equal to atx, where at is given by the matrix 0 1 minus 2 by t square 2 by t on any interval I not containing the origin. So, let x is equal to x1 x2, and then we get x1 dash x2 dash is equal to 0 1 minus 2 by t square 2 by t into x1 x2. Expanding this system, we will get x1 dash is equal to x2 and x2 dash is equal to minus 2 by t square x1 plus 2 by t x2. So, what you do is you just multiply this matrix with this one, and if you do that, 0 into x1 plus 1 into x2, which gives this x2, minus 2 by t square into x1 and 2 by t into x2 gives you this right hand side, and in the left hand side, as you can see, this is x1 dash and x2 dash, and you get this whole system. This can be expressed in the form t square x1 double dash minus 2t x1 dash plus 2 x1 is equal to 0, and you get this equation just if you differentiate this first equation, you will get x1 double dash is equal to x2 dash, and then you substitute this x2 dash here and you get this equation number 3. Let x1 equal to t to the power r, and we put this value of x1 in this equation 3, and if you do that, we will get r into r minus 1 minus 2r plus 2 equal to 0, and if you factor this, you will get r minus 1 into r minus 2 equal to 0. That is, the value of r is 1 and 2, and therefore, we get x1 is equal to t square, x12 is equal to t, x21 is equal to 2t and x22 is equal to 1. So, the meaning of this is our two solutions x1, the first one is t square, which is obtained by putting r equal to 2 here, and x1, the second solution, is obtained by putting r equal to 1, and so x1, the first solution, is t square, the second solution is t. And the second one, since x2 is equal to x1 dash, all we have to do is differentiate these solutions, and if you do that, your x21 is just the differentiation of t square, which is 2t, and x2, the second solution, is just the differentiation of t, which is 1. And hence, we have x1t is equal to t square 2t and x2t is equal to t1, and hence we get xt is equal to t square t 2t and 1, which is our required solution. Let us take another example where we have to find the fundamental metric solution of the system of the differential equation given by dx dt is equal to Ax, where A is equal to 1 minus 1 4, 3 2 minus 1 2 1 minus 1. Now, it can be easily checked that e to the power t multiplied by the column vector minus 1 4 1, e to the power 3t multiplied by 1 2 1, and e to the power minus 2t multiplied by minus 1 1 1 are three linearly independent solutions of the system of equation 4. So, how do you get that? So, all you have to do is consider this matrix and find the eigenvalues, and those eigenvalues you will see to be 1, 3 and minus 2. Once you do that, you calculate the corresponding eigenvector corresponding to the eigenvalues 1, 3 and minus 2, and you will get those solutions to be minus 1 4 1, 1 2 1 and minus 1 1 1, and hence you can say that these three are linearly independent solutions of 4. And then it is easy to get your xt as your fundamental matrix of 4. So, all you have to do is the first component will be minus e to the power t, the second component will be e to the power 3t, third component will be minus e to the power minus 2t. Next, it is 4 e to the power t, 2 e to the power 3t and e to the power minus 2t. Like that, we will get the fundamental metric solution of 4 as xt, which is equal to e to the power t minus e to the power 3t minus e to the power minus 2t, 4 e to the power t, 2 times e to the power 3t, e to the power minus 2t, e to the power t, e to the power 3t, e to the power minus 2t. And hence, we have the lemma: a solution matrix xt is a fundamental metric solution of the differential equation 1 on an interval I if and only if determinant xt not equal to 0 for all t belongs to I. The proof is very simple. Since the determinant of xt is not equal to 0 for all t belongs to the interval I, then the columns are linearly independent on I, and hence xt is the fundamental matrix of 1 on I. A matrix may have its determinant identically 0 on some interval, although its columns are linearly independent. We consider phi t is equal to 1 t t square 0 2 t 0 0 0, and since the third row all the elements are 0, it is very clear that the determinant phi t is equal to 0 for all t, and yes, the columns are linearly independent. So, in view of the above lemma, we can conclude that the columns of the matrix cannot form a solution matrix for equation 1. We next move to lemma 2. If capital Xt is a solution matrix of 1 on an interval I and T0 is any point on I, then determinant of Xt not equal to 0 for each t in I or never 0 on I. The proof is as follows. We denote the columns of x by x1, x2 dot dot xn. Let xj have components x1j, x2j dot dot xnj. Since xj is a solution of 1 on the interval I, it can be written as x dash ij is equal to summation k equal to 1 to n aik xkj, where I and j is equal to 1, 2 dot 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 n. Now, we recall a property on the derivatives of determinant x, which says that the derivative of determinant x is a sum of n determinants. So, if we differentiate determinant x, we will get this is equal to, the first is the determinant whose first row are all derivatives, that is x11 dash, x12 dash dot dot x1j dash dot dot x1n dash, plus the second one will be with second row all are the derivatives, that is we will get x21 dash, x22 dash dot dot x2j dash dot dot x2n dash and so on. So, the last one is going to be having the last row in terms of derivatives, that is xn1 dash, xn2 dash dot dot xnj dash dot dot xnn dash, and this can be easily proved by induction. So, right now we take it as a property and name it as equation 6. And hence, we use equation number 5, which says that xij dash is equal to summation k equal to 1 to n aika xkj. So, what we will be doing is we will be replacing this x dash 1 1 by this particular expression 5, which is equal to x dash 1 1 is equal to a1k x k1 k equal to 1 to n. Thus, we are using 5 to get determinant x dash is equal to summation k equal to 1 to n a1k xk into summation k equal to 1 to n a1k xk2 and so on. The same thing for the second determinant, where we replace the second row by summation k equal to 1 to n a2k xk1 summation k equal to 1 to n a2k xk2 and so on. And likewise, the last determinant, we replace the last row by summation k equal to 1 to n ank xk1 summation k equal to 1 to n ank xk2 dot 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 summation k equal to 1 to n ank xkn. We now use elementary row operations and we get determinant x dash is equal to a11 determinant x plus a22 determinant x plus dot dot ann determinant x for every t on the interval I, and hence we can write this as determinant x dash is equal to summation k equal to 1 to n akk t into determinant x, which is a first order scalar equation for determinant x. Thus, in view of the above result, we now reformulate our previous lemma about the fundamental metric solution of 1. So, the reformulated lemma is a solution matrix x t is a fundamental metric solution of the differential equation 1 on an interval I if and only if determinant x t 0 is not equal to 0, where t 0 belongs to I is an arbitrary point of I. So, we have given the basic definition of fundamental metric solution, and we have taken up some examples so that the definition is clear. Now, we will be look into some theorems on fundamental metric solution along with some very good examples. For the autonomous system of linear equation, we have the following result. A matrix x t is a fundamental metric solution of x dash equal to a x if and only if x dash t is equal to a x t and determinant x 0 not equal to 0. The proof is as follows. Let x I equal to 1, 2 dot dot n denote the n columns of the fundamental matrix x t. Then x dash t is equal to x 1 dash x 2 dash t dot dot x n dash t, and a x t is equal to a x 1 t a x 2 t dot dot a x n t, so that x I dash t is equal to a x I t for each I equal to 1, 2 dot dot n, which shows that capital X dash is equal to a x t, and the n system of linear equations x I dash t is equal to a x I t for each I equal to 1, 2 dot dot n are equivalent. Also, n solutions x 1 t, x 2 t dot dot x n t of x dash equal to a x are linearly independent if and only if x 1 0, x 2 0 dot dot x n 0 are linearly independent vectors of R n, that is determinant of x 0 not equal to 0, and hence the proof follows. In our next lemma, we have to prove that the matrix valued function e to the power a t is a fundamental metric solution of x dash is equal to a x. So, the proof in e to the power a t, we first expand it and we get e to the power a t is equivalent to I plus a t plus a square t square by 2 factorial plus dot 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 a to the power n t to the power n by n factorial plus dot dot dot. Please note, this is just an expansion of e to the power x. The only difference is here in the power there is a matrix, and hence instead of 1 we have replaced it by the identity matrix I. And this can be easily checked that if you differentiate this side with respect to t, we get d d t of e to the power a t, which is equal to a plus a square into 2 t by 2 factorial plus dot dot a to the power n n t to the power n minus 1 by n factorial plus dot dot dot, and if you simplify this, it can be written in the form a times e to the power a t. Also, determinant of e to the power a 0 is equal to 1, which is not equal to 0, and hence by the previous lemma e to the power a t is a fundamental metric solution of x dash equal to a x. In our next lemma, we have to show that if xt is a fundamental metric solution for the linear system 1 on the interval I, and capital C is a non-singular constant matrix, then xt into C is also a fundamental metric solution of 1 on I. Also, let yt be another fundamental metric solution, then it is also of the form xt into C for some non-singular matrix capital C. If xt is a fundamental metric solution, then x dash equal to Ax, and so is x into C for any matrix C, as xc dash is equal to x dash is equal to Ax into C is equal to A into xc. Now, determinant xc is equal to determinant x into determinant C, which is not equal to 0, as C is a non-singular matrix and hence x is a fundamental metric solution. Since xt and yt are both fundamental metric solution of 1 on the interval I, let xj be the jth column of x. Since xj is a solution and columns of y forms a set of n linearly independent solutions of 1, so xj is equal to summation I equal to 1 to n Cij yi, which we write as capital Y into capital Cj, where capital Cj is an n cross 1 column vector whose elements are C1j, C2j dot dot Cnj, and is a constant vector for each j equal to 1, 2 dot dot n. Therefore, if C is equal to C1, C2, dot dot Cn, then capital Xt is equal to capital Yt into C. Since both Xt and Yt are fundamental solutions, so determinant C is not equal to 0, which implies that capital C is a non-singular matrix. We next state the theorem, let xt be a fundamental metric solution of the differential equation x dot equal to Ax. Then we have to show e to the power at is equal to xt into x inverse 0. The proof is as follows. Let xt be a fundamental metric solution of x dash is equal to Ax. Then using the previous lemma 6 and the fact that e to the power at is also a fundamental solution, we have e to the power at is equal to xt into C. Let t equal to 0 in 7 and we have I is equal to x0 into C, which implies C is equal to x inverse 0. Hence, we have the result e to the power at is equal to xt into x inverse 0. We next look into an example where we have to find e to the power at given a equal to 111,032,005. To find e to the power at, we will use the result of theorem 0.1, and for which we need to find a fundamental metric solution. Now, please note this A here is an upper triangular matrix, and hence the diagonal elements are the eigenvalues of A. That is, the eigenvalues of A are lambda equal to 1, lambda 2 equal to 3, lambda 3 equal to 5. Otherwise, you can use the standard method to calculate the eigenvalues of this matrix. Since we have 3 distinct eigenvalues, so the corresponding eigenvectors are also going to be linearly independent eigenvectors, and hence they will form a set of 3 linearly independent solutions. Now we calculate the corresponding eigenvector corresponding to the eigenvalue lambda 1 equal to 1. And previously explained, and it can be easily checked, that 1 0 0 is an eigenvector in this case, and therefore we conclude one solution corresponding to lambda 1 equal to 1 is given by x 1 equal to e to the power t into 1 0 0. And as explained before, please note that this eigenvector is not unique, there can be any other eigenvectors also, and in that case this 1 0 0 will be replaced by that particular eigenvector. Similarly, solutions corresponding to lambda 2 equal to 3 and lambda 3 equal to 5 are given by x 2 equal to e to the power 3t 1 2 0 and x 3 equal to e to the power 5t multiplied by the column vector 1 2 2 respectively. Since the eigenvalues are distinct, so by theorem 1.4 the corresponding eigenvectors are linearly independent, which implies the linearly independentness of x I t I equal to 1 2 3. Therefore, the fundamental metric solution of x dot equal to A x is given by the matrix x t, which is equal to e to the power t, e to the power 2 t, e to the power 5 t, 0, 2 e to the power 3 t, 2 e to the power 5 t, 0, 0, 2 e to the power 5 t. To find e to the power a t, we use the result of theorem 0.1, which says e to the power a t is equal to x t into x inverse 0. So, it can be easily calculated x inverse 0, and the value is 1 minus half 0, 0 half minus half 0 0 half, and therefore, e to the power a t will be given by x t into x inverse 0, which is e to the power t minus half e to the power t plus half e to the power 3 t minus half e to the power 3 t plus half e to the power 5 t, 0 e to the power 3 t minus e to the power 3 t plus e to the power 5 t, 0 0 e to the power 5 t. Summing up, in this module we have discussed about fundamental metric solution. We have also learned few lemmas, and we have learned how to find the value of e to the power a t. In the next module, we will learn some different methods of calculating the value of e to the power a t, namely Putzer's method and other alternating methods. Thank you.